Okay, section 3.5 is called Complex Numbers in Polar Form, de Moivre's theorem. Okay, let's start by talking about and reminding ourselves, or actually maybe this isn't a reminder, maybe this is the first time you've ever heard of a complex number. Well, just to kind of like fast track it, a complex number is a number in this form, or it can be in that form, I guess I should say, considering what's in our future. But do you notice this right here? That is an I. Do you remember what this means in mathematics? Do you remember what you learned about I? It's the imaginary number of like the square root of -1. So a complex number is a number that could have a real component and also an imaginary component. So that's what this a plus bi is all about. Like a and b would both be numbers, so a would be like the real component and bi would be like the imaginary component, okay? And so I guess if a was 0, then we would have what would be strictly an imaginary number. And if b was equal to 0, then we would have a number that was strictly real. So I guess in a way what I'm saying is both real numbers and imaginary numbers, or maybe I should say like numbers that are purely real and numbers that are purely imaginary, all of them fall under the complex number umbrella. And our first thing here real quick in section 3.5 is to graph complex numbers. Well, I guess I'm going to draw a quick comparison back to like middle school, where you were like graphing numbers, and specifically maybe you were graphing negative numbers on the number line. So if you were to graph like -5.5 on a number line, you would just draw a dot at -5.5, like on the number line. Well, having a number that's complex, we can't just have a number line. We actually need a plane. So I know it's kind of weird, but we're going to plot a point in what we call the complex plane. And it's not like we're plotting coordinates per se. We're plotting a number. But we need a real axis and an imaginary axis. And so we take the a value and we plot that like on the real axis, and then we take the b value and we plot it on the imaginary axis, and that would be where we plot our complex number. And I guess we're going to be using the letter Z a lot to represent complex numbers. And so let's see how this works. Let's say you were given this Z value, or this complex number, 2 plus 3i. Well, this is the real axis, so we go to 2. And then the imaginary axis, we would go to 3 and plot right there. So it'd be like your a value is 2 and your b value is 3. Here your a value would be -3 and your b value would be -5. So we go to -3 on the, I guess you could call it the a axis or the real axis. Then you go down 5 on the imaginary axis. And that would be where -3 minus 5i is. And you don't really need a z necessarily, but I guess if you said like z equaled that, then you'd be plotting z. But you're really just plotting negative 3 minus 5i. Just like over here, when we were plotting z, but I guess specifically we were plotting 2 plus 3i. Z equals negative 4. We don't have an I, do we? So, I mean, I guess A would equal negative 4, and technically our B value would be 0. So we go negative 4 on the real axis, 0 on the B axis, or the imaginary axis. Kind of like over here where it doesn't look like we have an A value, or we could say A equals 0, and our B value looks like negative 1. And so we end up plotting it right there, like on the 0 on the A axis, negative 1 on the B axis, which again is more like real and imaginary axes. Next, we're going to talk about absolute value of a complex number. I mean, do you remember what absolute value means of like regular numbers, like just real numbers? Do you remember the official definition of absolute value, like you would find, like the definition you would find in a textbook or something? If you don't, it is the distance from 0 on a number line. Well, we don't exactly have a number line here, like think about the distance from 0 of this complex number. And yes, 0 would be the origin, 0, 0. Do you know how we would find the distance from 0? It's very, very, very possible that the distance away from 0 for a complex number is a diagonal distance, right? So it makes a lot of sense that we invoke essentially what is the Pythagorean theorem. So yes, what I'm saying is finding the absolute value of a complex number pretty much boils down to finding the length of a radius, of a hypotenuse, like the diagonal of a right triangle. And that's literally what this is. It's the Pythagorean theorem. It's the distance from the origin for any complex number. And so example A, all you have to do is take your A value of 5 and your B value of 12. I mean, think about it. We'd be going, if you had to graph this, you'd be going like over 5 on the A axis, the real axis, up 12. And so you'd be essentially doing the Pythagorean theorem to find C or your R or whatever you want to call it. And the final answer would end up being 13. Try this one on your own. Example B. Pause the video now and try this on your own before I move on. Alright, now that you've probably unpaused the video, right? You would plug it into what's essentially the Pythagorean theorem and get the square root of 13 as your absolute value. Okay? Which that's the bestest answer you can do right there, the square root of 13. Next, we're actually going to, oh my goodness. Last section, 3.3, we learned about polar coordinates and like polar form. And yes, we're now going to take this like complex number stuff and also throw in this whole polar form stuff. Well, you totally can, because with A and B from like your, what form would we call this? A plus BI would be our rectangular form. So A plus BI would be called rectangular form, and we want to talk about what would be polar form. Well, we can do that pretty easily because, I mean, looking at a polar plane, isn't A and B pretty much the same as having X and Y? So think about last section where we were turning X's and Y's into R's and Thetas. Couldn't we use the same mathematics to turn A and B into R and Theta, because it's like the same picture, okay? Or did I say polar plane? I don't know. Like the complex plane, right? Because the complex plane is also a plane, just like the XY plane is. So again, A and B are totally like X and Y. So what could we say A was equal to? Think of last section. A is just like X. So couldn't we just say A equals R cosine of theta? Just like last section, we totally went a lot with the fact that X equals R cosine of theta. And so B we could say is R sine of theta. Which means when we talk about, okay, so now we could say that A, like A is R cosine, and the B over here, BI, the B is R sine. So this would be like saying A plus BI. And so, just like that, something that was in rectangular form is now in polar form. But what we're actually going to do before we give what final polar form is, we're going to factor out an R. You see how both of these have an R? We're going to factor out an R, and this is what we're going to be going with. Like when you think of a complex number that's in polar form, you should think of this right here. R times the quantity cosine theta plus I sine of theta. And yes, by the way, since A and B are like X and Y, A squared plus B squared would be R squared. And the tangent of theta would be like, like what? Y over X? Same thing. Whoa, wait a darn second. Wow, I wonder if I'll notice that in class. Bonus point potentially if I don't see it. What the heck? Yeah, B over A, because tangent of theta is Y over X, not the other way around. Okay, here we go. First example here coming off of that stuff. Let's plot this in the complex plane. That's easy. It's like your A value is -1 and your B value is -√3. So we go to -1 on the real axis, -√3 on the imaginary axis. Well, that's like about -1.7-ish. So whatever, right? About right there. About right there. So we go to the left one and we go down like 1.7-ish. So, but then we have to write Z in polar form. So that's rectangular form. We want polar form with the R and the theta. Here's how we're going to do this. If we know A and B, just like last section, just like having X and Y, we can find R. If we know A and B, we can find R by doing what's basically the Pythagorean theorem. And we've done this many a time, haven't we? And so what's R going to be? Well, we got to take the square root of both sides and get 2. Plus or minus 2, but we're going to positive 2 is what we go with. So there's R. So, I mean, eventually we're going to want to plug into polar form. So it looks like my R is going to be 2. But we also need theta. How are we going to get theta knowing A and B? Well, like this. And darn it, again. Ugh. What brain was out to lunch or something. Right? I wonder if the whole darn thing is wrong now. Let's see. So, my beaver. Oh my God. My God. That's not right. And that's not right. What you should have is what? So b is negative root 3 over negative 1. And so it would overall be that. And once you know that the tangent of theta is root 3, and then you're thinking, okay, what would that make theta? Well, now you just go to your cheat chart, and your cheat chart says what? That, let's get rid of this completely. So your cheat chart would say that theta could be 60 degrees or 240. Which one would it be? Which one makes sense if we're over here in quadrant 3? Okay. Wait a minute. That's not right either, is it? What does your cheat chart say? Check it for me, actually. Pause the video. Check your cheat sheet. The tangent of what equals root 3? Because we're over here in quadrant, so negative 1, right? And so hopefully we're getting that theta would be, oh, wait a minute, was that right all along? What a nightmare this is. $60 or $240 was correct. I don't know what I was thinking there. So negative root 3 over negative 1, overall root 3. And so theta could be 60 according to your sheet or 240. So which one makes sense if we're over here in quadrant 3 with our complex number? Well, it would be 240 would make sense. And so now that we know theta, we finish plugging into polar form. So the final answer here is that. That is in polar form. R and theta plugged in for, okay, so there we go. Next, we're going to kind of keep the ball rolling with this polar form stuff, and we're going to investigate, what if we had, for example, two numbers that were in polar form, two crazy complex numbers that were in polar form. How would we find the product? Product means what? It means multiply. So a little bit of quick investigation. We'll probably be spending more time in class doing this. Maybe, maybe not. But to fast track the video, this would start by multiplying the R1 times R2 together. this complex number had a radius in R1. This complex number had a radius of R2. And so the radii multiply together, and then as far as the bubbles, that's going to be FOIL. And basically, we get to, once we get to here, we're going to kind of go, yeah, yada, yada, yada. So, looks like what I did here was I grouped the i's together, as well as notice that I squared is equal to -1. If you remember that from Algebra 2. Remembering that I is the square root of -1. If you do I squared, you just get -1. So realizing that, and then putting these two together and factoring out an I get myself here. But look, I'm trying to fast track this, especially right now, because the bottom line is that you end up with this as like a final formula for the product of two complex numbers that are in polar form. This purple formula will end up on a formula sheet that you will have on the test eventually. And if you look at what the final formula is, man, it ends up being so simple, right? You just take the two numbers you were given, and you have to multiply the radii together, and then just add the two angles. Theta1 plus theta2. So watch how this ends up working out. So here's an example. Let's find the product of these two complex numbers that are in polar form. When you just go right to the formula, R1 is 6. The other radius, the second radius, R2 is 5. And then theta1 is 40. Theta2 is 20. So look, at the end of the day, you're just going to be doing 6 times 5 to get 30, and 40 plus 20 to get 60. For both the cosine angle and the sine angle. And so as that sinks in for a second, how easy that was, right? This formula just says like, hey, multiply the two radii together, add the two angles together for your final answer in polar form. And that's what they wanted, look, right here. And so for this problem in these directions, this is the final answer. But what if I wanted the final answer in the other form, rectangular form? Here's what you would do if the directions requested the final answer to be in rectangular form. All you would do is do this, like do the cosine of 60 and do the sine of 60. That was probably like your original instinct already. Like think, wait, shouldn't we do the cosine of 60 and do the sine of 60? Well, no, if what you wanted was to keep it in this form, you wouldn't. But if you wanted to turn it into rectangular form, you would do the cosine of 60. Just look at your sheet. Cosine 60 is 1/2. Sine 60 is √3/2. And what you would do next is, look, distribute the 30. Like so. Now you would distribute the 30 through the bubble, and you would get that. And so if they would have wanted rectangular form, you would have given this as your final answer. But once again, like if they want polar form, this is the final answer. Hey, no cute like build up here. Like see how the all this blue and red build up to get to purple. Now we're just jumping straight to purple, man. So let's just cut right to the chase with the quotient. What if I wanted to divide a couple of complex numbers in polar form? This would end up being the formula. And look, all you would have to do is divide the two radii, the two radiuses, and subtract the first angle minus the second angle. And that's the formula. Again, feel free to, as always, pause the video if you need more time to write down stuff, obviously. But I'm moving on to the example where let's find the quotient of these two complex numbers that are in polar form. And yes, they want the final answer to be in polar form. So we're going to leave our final answer in polar form. Now, again, all we got to do is divide the first radius divided by the second radius, and then take the first angle, which is 4 pi over 3, minus the second angle. Now I wonder if I made it a point to change the radian measures to degrees. Yes, I did. And you probably want that also. And you might have thought to do that also. The only thing left to do is, what is 50 divided by 5? What is 240 minus 60? Boom, done. But real quick before we move on, could you have left the angle measures in radians? Of course. You know, you could have done 4 pi over 3 minus pi over 3, and that would have eventually gotten you pi. So could you have had pi here and here instead of 180 degrees? Of course. But you probably went with this. Or you probably prefer this. Man, next thing. So we've done product. We've done quotient. What if we wanted to raise a complex number to a power? Well, let's do a little bit of cutesy build-up to the final punchline. So right here is going to be the punchline. Is it in purple? Yeah, it's in purple. That's the color, I guess, for now. But, okay, so what if you had a complex number z? What would it mean to raise it to the second power? Well, it looks like we would end up getting this, right? Because you do r times r and you add the powers, right? This is back to the product formula, isn't it? You multiply radius times radius to get that, and you add, right? That goes back to this formula. Now, so z squared would be this. Okay. What if we wanted z to the third? Well, that'd be like this, right? And so we multiply the two radii together to get that, right? R squared times r. And we add the angles to get that. Likewise, this. Do you see a pattern? Well, what if we wanted to raise z to any power n? We do this. So this is the overall formula for raising something like this to whatever power you wanted, the n power. And so the formula basically says that all you have to do is raise the radius to that power, but multiply the angle by n. And so putting this into practice, let's say we wanted to take this complex number z and raise it to the fifth power. All we have to do is take the radius, well, there's the formula again, take the radius and raise it to the fifth power, and take the 30-degree angle and multiply it by the 5. Very simple formula, right? So what is 2 to the fifth power? That's 32. And then we just have to do 5 times 30 degrees to get 150 degrees. And that's that. So 3 very simple formulas so far, right? This very simple formula to do a product. Multiply the radii, add the angles. This very simple formula to find a quotient. So you divide the 2 radii and subtract the angles for your final answer. And then a very simple formula to raise a complex number to some power. So you raise the radius to that power, but you multiply the angle by that power for your final answer. We have one more thing we're going to do, one more crazy thing with complex numbers in polar form. And we're going to talk about roots. So here we go. First, real quick, pause the video, and I want you to raise this to the 6th power. Go. Well, if you're going to raise this to the 6th power, wouldn't you just take the radius and raise the 6th power, but then multiply the 20-degree angle by 6 to get 120? Okay? So that was like the formula we just learned. Raising complex numbers in polar form to a certain power. Here it was the 6th power. So you just follow the formula. And all 3 of those formulas, not just the product one, they're all going to be on the formula sheet. Now, before I reveal these boxen, let me kind of relate it back to when you first learned about, say, square roots. So why, really why do you say that 7 is the square root of 49? In other words, the second root, right? 7 is a second root of 49. Why? Well, it's because 7 to the 2nd power is 49. If 7 to the 2nd power is 49, you can say that 7 is a second root of 49. So if this to the 6th power gets you what's here in royal blue, then this you could say is a complex what root? Not a second root, but a 6th root of what was in royal blue here. Okay? I mean, right? So we're going to be doing complex roots. And it's a formula. And so if we want to find complex roots of a complex number, then we use this purple formula. Or this blue formula where instead of 360 degrees, we use radians. I mean, and you're very most likely going to want to go along with the class and with me, where we're going to be using degrees. So we're going to be using the purple one. But technically you could use radians, and so it wouldn't be 360; it would be 2 pi. But we're going to be using the purple one. Now, if we are given a complex number just like this, and we're asked to find all of the nth roots, all the 3rd roots or the 4th roots or the 5th roots, then as we think about how we're going to plug into this formula, The n is going to be like what kind of roots we're finding. The r is going to be the radius, duh. Theta is going to be the angle, duh. There's n again, 360. So the only thing I haven't addressed yet is what are we going to be plugging in for k? For k. All right? Now, check this out. If I was going to ask you to find all of the fourth roots, think about what I just said. All of the fourth roots. All of them. How many are there? Well, that's actually really easy. There are 4 total fourth roots. How many sixth roots would there be, you think? That's right, 6. Okay? So it kind of says right here, there is n, look, there is n distinct nth roots. That's where the k comes into play. Like if I ask you to find all of the fourth roots, you're going to have to do this formula 4 times. 4 times you do this formula. But each time you're going to be plugging in the same n, the same r, the same theta, but you're going to be plugging in a different k value for each of the different fourth roots or whatever roots. So that's why we kind of say like k equals 0, 1, 2, dot, dot, dot. All right? In fact, I don't want to leave it just like that. Let's so let's write that a little nicer, I suppose. So for k equals 0, 1, 2, 3, dot, 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 until you got to, actually, not n minus 1. Because we're starting with 0, okay? For the very first root, you're going to be plugging in 0 for k. And so, again, let's talk about what if we were finding all the fourth roots. You would want 4 total roots. So you wouldn't go all the way to k equals 4. You would actually stop at k equals 3, because that would be then 0, 1, 2, and 3. That's 4 total roots. Okay? And here is an example of that in action. Oh, here we go, fourth roots. So find all of the complex fourth roots of this guy. So once again, we're going to use this formula, but z sub k, right? So the formula was z sub k, and so there's going to be 4 total roots, where we let k equal 0, the root where we let k equal 1, the root where we let k equals 2, and the root where we let k equals 3. So 4 total roots, 0 through 3. And each time we do this formula, we're going to be plugging in 4 for n. So right here and right here and right here. Okay? 16 in for r. Yeah? And 120 in for theta. Okay? But each time we do this formula, we're going to be plugging in a different value for k. So what are we plugging in here? Well, for this one, 0. Right? And so the fourth root of 16, I guess there's a way to do that. There's probably a way to do that on your calculator, just like that, with like the radical symbol, where you can do like a different kind of root, you know, like for a number. But your other option is, you know, remembering that the fourth root is the same as a 1/4 power. So if you were to raise 16 to the 1/4 power, that would be the same as doing the fourth root, and that would be 2. And then everything in this giant parentheses right here, 120 plus 360 times 0 over 4 is 30. And so my first final root is this, my k equals 0 root. And then I got to do this again, but this time I let k equal 1. So everything's the same. Look, in blue, everything's the same. N and R and that's N and that's theta. But the k value is now going to be 1. Obviously, this is still going to get you 2. But now this mathematics ends up being 120. So right here would be my second complex fourth root out of 4 total roots. Now look, I didn't even bother writing because it's going to be the same, like, right? So look, again, I know this is going to be 2, but the only thing different is my k value is now going to be 2, and I know I'm just going to be writing the same exact thing, and all of this mathematics, 120 plus 360 times 2, all divided by 4 will get you 210. And this is also going to be 210, right? And so here is my third out of 4 complex fourth roots. And man, to even fast track this even more, to find my root where k equals 3, again, the only thing that gets changed was this answer. 30 becomes 120, 210. So look, this is all that really matters as we change what k equals. So now k would be 3, and so my angle would be 300. This is going to be 2 again, right? So here is my fourth root. Well, my fourth complex root out of 4. Okay? And that is section 3.5.